All right, welcome to the Explainer. Today, we're tackling one of the most frustrating bottlenecks in modern development, which is bridging that massive gap between incredibly powerful local AI models and, actual real-world utility. We're going to see exactly how combining Qwen3.6 and model context protocols lets us build systems that don't just sit there and think, but actually do things.
It's a question literally every developer building with local AI hits eventually. You've got this amazing local model, right? It reasons beautifully, it writes rock-solid code, and it can parse some seriously complex logic. But then you have this realization. What good is a genius AI if it can't actually do anything? It's like having an incredible brain, but absolutely no hands. The source material refers to this as the cloud wall. You have this super powerful local model, but it's completely trapped inside a terminal. It can't query your internal database, it can't open a GitHub issue for you, it definitely can't call your internal CI/CD API. Historically, getting past this wall meant writing endless, soul-crushing Python wrappers for every single tool. And then, of course, you have to maintain that brittle glue code every single time an API changes. Nobody wants to do that.
Okay, let's dive into this. Here is our roadmap for today's Explainer. First, breaking the cloud wall. Then, Qwen3.6, the Agent King, followed by hardware and software setup, understanding model context protocol, building the GitHub Assistant, and finally, optimizing your local agent.
Starting with Section 1, breaking the cloud wall, the key to local utility.
So the real solution to our trapped AI problem isn't more custom wrappers. It's the Model Context Protocol, or MCP. Designed as an open standard by Anthropic, it essentially acts as a universal, pluggable nervous system for AI tool connectivity. The absolute magic here is that you define a tool just once as an MCP server. From that exact moment on, any MCP-compatible client, model, or framework can discover and call that tool with zero custom integration code. It completely wipes out the need for hard-coded glue. Let's move to Section 2, QW3.6, the Agent King, the perfect brain for local agents. The naming convention of this model tells you exactly what you need to know about its capability. It boasts 35 billion total parameters. This gives the model just a massive, deep well of knowledge and reasoning capability to draw from whenever it's handling complex development tasks. But here is the real aha moment. The A3B in its name means it only activates 3 billion parameters per pass. Because it's a mixture of experts model, meaning it only routes tasks to the specific parts of its brain that are actually needed, you get 35 billion parameter reasoning power for a fraction of the compute cost. That is exactly why it fits right on consumer hardware that would normally just collapse under a dense 35B model. Now check out this massive number. 262,144. That is the native token context window. And look, for an agent reading source files across an entire repository, maintaining a history of tool calls, and tracking a multi-step plan, context length isn't a luxury, it's a strict operational necessity. Most smaller models cap out early, they lose their history, and they start hallucinating mid-task. Qwen3.6 actually has the headroom to keep absolutely everything in mind. Let's see how this builds on its unique architecture. Qwen3.6 uses a pretty fascinating 3-to-1 ratio in its 40-layer stack. It interleaves gated delta net, which is a linear attention mechanism that super efficiently processes massive sequences with traditional gated full quadratic attention. This combination is literally lethal in the best way possible. It allows the agent to efficiently chew through a 500-file repository using linear attention while still applying precise, deep relational reasoning on the most critical sections using that quadratic attention. All right, on to Section 3, hardware and software setup, bringing the system to life. Now, the deployment path you choose here depends entirely on your hardware. If you've got an RTX 4090 with 24 gigs of VRAM, you can run the Q4 quantized version incredibly smoothly. Got an A100? You can run full blow 15. But what if you don't have a massive GPU? Well, you can use K-transformers, which offloads to the CPU and system RAM. You're going to need about 64 gigs of system RAM for that, and yeah, latency drops to maybe 30 to 120 seconds a turn, but the text notes this actually works perfectly for background tasks. And hey, for peer testing, you can always swap in a smaller model like Qwen2.5 7B using All-Amma. Once you pick your deployment path, you have to serve it. The goal is simple. Create an OpenAI-compatible API running directly on localhost.
SGLang is highly recommended here because it handles long context agent workloads beautifully, but vLLM is also an incredibly robust alternative. Whatever you choose, listen to me. Do not move forward until you can curl your localhost and get a valid JSON response with a choices array back. Getting the serving layers solid first will save you massive headaches later on, for sure.
Moving to Section 4, Understanding Model Context Protocol. Deep dive into JSON RPC 2.0.
The absolutely crucial point is understanding this exact flow, because MCP is a JSON RPC 2.0 protocol. The client calls tools/list to discover what's even available. The model reads these schemas and decides what to do. But crucially, the model does not execute the tool. It just emits a structured call. The client executes it by sending a tools/call request to the server, and then the server does the actual work. This brilliant separation of concerns means your code never hardwires a specific tool to a specific model ever again. Okay, Section 5, Building the GitHub Assistant, from theory to execution.
So, you have two main paths to build an agent, like a local GitHub Developer Assistant. Path A is using the Qwen agent library. This is your fast path. It abstracts away tool discovery, parsing, and multi-turn management. It's totally perfect for rapid prototyping. But if you are building a production system, we need to monitor every single message, log every tool call, and strictly control retry logic. You want path B, using the raw MCP Python SDK with mcp.client-session. It's a bit more code, but it gives you total, fine-grained control. And the absolute beauty of MCP is that you are not limited to pre-built tools for GitHub or file systems. You can write custom MCP servers to bridge literally any gap in your workflow. Need to run code analysis? Just write a code quality server that wraps rough and PyTest. Need internal database access? Expose it via an MCP server. You just build it, test it standalone, and then plug it straight into your agent server config. This is where the real power gets unlocked.
Section 6, Optimizing your local agent. Thinking mode versus mechanical mode.
To make this efficient, you need to toggle between thinking mode and mechanical mode based on the specific task. In thinking mode, the model generates a deep chain of thought trace. This is brilliant for planning or debugging multi-file refactoring, but it costs thousands of tokens and adds significant latency. For simple mechanical tasks, stuff like list directory, read file, write file, you really should switch to mechanical mode. It skips the reasoning trace, drastically reducing latency without sacrificing any quality for unambiguous loops. Just remember to switch this per request, not globally.
Which brings us to the preserve thinking flag. When you set this to true, the model retains its reasoning traces in what's called the KV cache, which essentially acts as its short-term memory. If it makes a solid plan in turn 1, it doesn't waste compute rederiving that exact same plan in turn 4. If you're using serving infrastructure with prefix caching active, this drastically improves your tokens per second rate. A good rule of thumb, turn this on for any session longer than 5 turns. By combining Qwen3.6's incredible architecture with the universal connectivity of MCP, the GitHub Assistant we just discussed is literally just the beginning. The exact same architecture applies to a DevOps agent that reads CloudWatch logs to automatically open incident tickets, or a data pipeline builder reading SQL schemas to validate outputs, or even a research assistant querying vast academic databases. The ecosystem around this is growing incredibly fast. So, look at where we are. You now understand how to deploy a 35 billion parameter agent, fully equipped with universal tools, running entirely on your own local hardware. The cloud wall is officially broken. The tools are right there in your hands. So the only question left is, what impossible thing are you going to build tomorrow? Thanks so much for joining me on this explainer, and happy building.